We are the Florida Power and Light FPNL Exoskeleton team. Thomas, Caden, Musa, Christopher, and I, Ford Perry, have been working tirelessly on this project for the past 2 semesters. We have also been collaborating with the Mechanical Engineering Senior Design team who began a semester before us to ensure its success. We are proud to be working with FPNL, our sponsor, who has given us the opportunity to create an exoskeleton system that's tailored to enhance the work of their field workers. Our main objective is to develop a lower body exoskeleton that will aid linemen in their day-to-day job of climbing utility poles while reducing physical strain. Our team is dedicated to making a difference in the lives of hardworking linemen, and we believe our exoskeleton system will do just that. We are excited to be a part of such a noble cause that seeks to improve the quality of life of individuals who work tirelessly to keep our homes and communities running. We're confident that our exoskeleton system will exceed expectations and prove to be a valuable asset in the power industry. Our goal is to develop a smart exoskeleton that incorporates motors and an advanced control system aimed at helping linemen climb utility poles with ease. Our primary objective is to reduce physical strain on the body and minimize the risk of injuries while ensuring optimal ergonomic support and safety. Our solution is to take inspiration from the work done by previous mechanical engineering team who worked on this project. They designed a framework in which we are to add a power and logic system to in order to make this a fully motorized exoskeleton. Here is a basic block diagram of our system as a whole, with 2 power sources, a 9-volt for the peripherals and a 20-volt for the motors. There is a control system loop incorporating the Arduino, sensors, and motor control boards, which will send signals down to the motors, telling them to stop and start. This diagram also outlines the team members' contributions and efforts to each component. Safety being our #1 value has made it our biggest goal to maximize the safety of use, ergonomics, and comfort of our device. Again, the main goal of this is to relieve as much stress on the user as possible while in use. We would also like to maximize mobility so that the user does not have to fight the exoskeleton to get where they want to be. Another objective is to create a cheaper alternative than the exoskeletons that already exist. Finally, we have the goal to include a user interface and the ability to control and adjust the device for user compatibility.
The specifications and requirements of this project are comprised of a comprehensive set of 8 deliverables, each playing a critical role in ensuring the success of the project. These deliverables encompass a wide range of functionalities, designed to meet the key criteria and ensure the development of an advanced exoskeleton system that can be utilized for climbing power poles in challenging conditions. One of the crucial aspects of the project is the development of a locking mechanism that allows for efficient and reliable locking and unlocking of the exoskeleton. This exoskeleton needs to be able to withstand harsh environments, such as extreme temperatures and adverse weather conditions. Furthermore, the system will have an ergonomic design that will allow users to comfortably use the exoskeleton. Deliverable 3 states that the system will have a safety feature that will detect if a user is descending too rapidly, as if they are falling, and shut down the system within a half second. The next deliverables show the need for the system to utilize cost-effective materials and parts that will be replaced when the need arises. The system will also be able to ascend and descend a power pole with various sizes of obstacles. Deliverable 7 mandates the provision of ample torque at the user's joints to enhance their climbing ability. This requirement emphasizes the need for the exoskeleton to provide sufficient assistance to the user's joints, enabling them to exert the necessary force for climbing with ease and efficiency. Lastly, Deliverable 8 emphasizes the development of a sophisticated control system that can accurately read the angle of the user's leg and compute whether the leg should be moving, while also transmitting signals to the motor with minimal delay. This control system needs to be highly responsive, with a rapid response time of less than 3/4 of a second, to ensure seamless coordination between the user's movements and the exoskeleton's motor functions.
The control system is comprised of 2 main components. The first component is the Arduino Mega 2560. The Arduino is a fairly cheap control board at $60 and has a lot of memory that it is able to handle, as well as a very high number of input and output pins. This allows us to attach all of the sensors and all of the control boards that are necessary for this project. The other control board that we were considering is the Raspberry Pi. The Raspberry Pi, at the size that we would need, is a little more expensive, around double the price, and it does not have as many pins on the control board. Therefore, we might not have been able to utilize that board with the number of pins that we need. The second part of the control system is the motor control boards. The motor control board that was chosen for the project is the Flipsky electric speed controller. The other motor controllers that were considered are the AITIAO controller and the electronic microcontroller. Both of these are cheaper PWM controllers that interface to the motor and battery through terminal blocks. They are both capable of carrying 16 amps of continuous current. The Flipsky board is a more expensive choice, but is able to carry a much higher continuous current of 50 amps. This allows our system to carry the required current to provide the torque the exoskeleton needs to help the user. The Flipsky control board communicates to the Arduino through dedicated signal wires. This control board is also capable of communicating to the VESC software. The VESC software is how we are able to test the motors and calibrate them to the necessary duty cycle and amperage for the system. It is also necessary to calibrate the PPM signals coming from the Arduino for the motors and motor control boards to be controlled directly by the Arduino. The control system is driven by the software shown, which is loaded onto the Arduino. Variables for the speed controllers, PPM signals, accelerometer values, gravity constant, fall detection counter, and knee joint angles must be created. There is then a setup and initialization period that the system must run through on power up. The accelerometers are first initialized by setting their pins and writing signals to begin communication from them to the Arduino. The motors are then initialized by sending the neutral PPM signal for a short period of time to each control board. The loop to run the system reads acceleration values and adjusts them for gravity. After this, the system is able to constantly check if the user has fallen. Using the acceleration values, the angle of the knees are calculated, as well as the change in angle. This information is used for the system to decide whether or not to take a step with the user and with which leg. The system takes a step by sending high or low PPM signals to the respective motor. This software allows the system to run as intended.
In this section, we are going to be discussing the electronic and mechanical peripherals of the exoskeleton, with the first of those being an electric motor. The electric motor that we have chosen is a brushless DC motor, which utilizes a Hall sensor, and that's going to provide the torque at the knee and hip joint. The type of brushless DC motor that we have chosen is the Flipsky brushless DC motor, and that motor is used for electric longboard enthusiasts. This, we have seen, has the best blend of torque and speed compared to the two other motors that we have decided between. Since it is used by electric longboard enthusiasts, this motor is mass produced, so it reduces the cost and increases the ability to find parts for it. Speaking of those parts, the motor pulley system we are integrating with the fact that the motor is for an electric longboard. This motor pulley system is going to direct power onto each of the joints and utilize a gear ratio to amplify the torque from the motor to the joint. We are going to be using a belt and pulley because they are durable and they are much easier to replace than something such as a bevel gear or any kind of gearbox. The pulleys that is coming from the motor is going to fit directly onto the motor shaft due to them being manufactured specifically for them. There's a model on the bottom of it showing how we are going to integrate the motor and the pulley onto the leg of the exoskeleton. Now, the aluminum exoskeleton frame that we are going to be using is the one made by the mechanical engineering team last semester, and this is going to be made of aluminum 6061, and it includes a backplate, hip joint, knee joint, and a plate to attach to the feet. Each of the joints has a modular length to incorporate for different heights.
Hip joints are made from a milled billet 6061 aluminum and are comprised of two pieces that form a rotating joint. For the hip joint, there is a hinge mechanism that allows for a full range of rotation in the interior-posterior direction. There is also a ball and socket that allows for limited motion in the medial, lateral, and superior-inferior directions. A mechanical locking mechanism will be incorporated within the frame. This must be mechanical to promote safety and provide a fail-safe if the electric components fail. This function can also be utilized as a way to lock the exoskeleton into a sitting position. One of the possible sensors that can be attached to the motors is the Hall effect sensor. A Hall effect sensor is a magnetic field sensor that works using the principle that when a wire with current going through is acted upon by a magnetic field, it will produce positive or negative voltage depending on the side. These sensors are either mounted to the stator or the rotor and are used to detect when a rotor has passed and if it is a positive or negative charge. Although this does not give the exact position a motor has turned to, it does allow for the motor to know which stator is supposed to be powered and will continue to provide power to that stator to overcome the stall torque faster than if there was not a Hall sensor. Another advantage is that the Hall sensors are cheap and are built into some motors. So if there is only the need for approximate positional sensing, the Hall sensor is superior. Optical encoders are the large, more precise sensor that can be integrated into a brushless DC motor. An optical encoder consists of a circular disc connected to a rotating shaft of the motor. Below the disc is an optical sensor that picks up the light as it pulses and goes through the transparent part of the disc. Using the signal of the optical sensor, the optical encoder can detect the rotational speed of the motor. Since the motor software has precise knowledge of the speed the shaft is moving, it can track where the shaft is located in degrees. This method requires more space than a Hall sensor, but provides a significantly more accurate reading. A Hall sensor is the cheapest and most space-efficient option between the two and would allow the motor control board and the software to have enough of an idea where the motor is turned to that it can provide the stall torque we need. We decided not to include an optical sensor due to the higher cost and space requirements and the fact that we will be able to use other sensors to know where the leg is extended to instead of needing to invest in an optical sensor. The accelerometer sensor is a superior choice over the sensor options. This is due to their exceptional versatility and accuracy in detecting movement, providing a comprehensive understanding of the overall body movements of the wearer, as opposed to SEMG sensors, which only monitor muscle activity. Accelerometers offer a more holistic perspective, which can be utilized to regulate the movements of the exoskeleton and sustain the wearer in an appropriate posture while climbing. Moreover, accelerometers possess the capability of detecting movement in 3 dimensions, thus presenting a comprehensive picture of the wearer's motion compared to load or pressure sensors. These sensors measure force and pressure respectively, may fall short in capturing the intricate movements and orientations imperative for safe and efficient climbing. In addition, accelerometers are renowned for their compact size, lightweight, and low power consumption, rendering them highly suitable for use in wearable exoskeleton suits. Their fast and responsive time and ability to accurately track rapid movements further ensure that the exoskeleton can promptly react to the wearer's movements and provide the required support. In decision, with their proficiency in accurately and effectively detecting body movements, accelerometer sensors are a premier choice for implementation in a lower body exoskeleton suit.
Now to discuss about the power systems. This section is what Ford and I will be covering and is the area we are in charge of. So what exactly is the power system? The power system that we are building is to power all of the device's peripherals from a battery pack. It is our job to make sure that there is enough power coming from the battery that the components such as the motor, control board, and accelerometer can work properly. We want to ensure that the exoskeleton receives enough power so that it can operate to its fullest potential. As you will see in the future slides presented by Ford, we made sure to have the power system be one of the most important parts of this build. If the power system is not working properly, or there is some sort of malfunction, this can cause some serious harm or be a potential danger to the user. Because of this, the design we have made is the best when it comes to user safety, in our opinion.
This is our power system block diagram. You'll notice a few components that do not necessarily sound electrical. This is in part due to being a contributor to an interdisciplinary project. alongside the mechanical engineering team before us, who played a role in designing and planning the frame and knee joints. Furthermore, we did not include a PCB in our design as we are maximizing commercial off-the-shelf parts as they are more safe and reliable. We also intend for our project to be replicated by future generations of senior design projects and by FPNL themselves. This move has been approved by the Department of Electrical and Computer Engineering, as well as our advisor and our sponsors. Based on our requirements of roughly 1 hour of use time and the motors drawing roughly 1.3 amp hours, we concluded that a lithium-ion battery would best suit our needs. These batteries are compact, yet efficient and safe, easy to charge, and readily available. After testing and experimenting, we decided to go with a DeWalt 20-volt 2 amp hour battery for each motor. These batteries are often found on job sites, most people are familiar with them, and they are extremely easy to replace and charge. Here is a detailed block diagram of our power system. We broke the system down into 3 phases, as the peripherals of our system could not operate on such a large battery. Phase 1 is a low-powered electronic accessory power system. This system is powered by a single 9-volt battery and then regulated by an adapter chip. From here, power is sent to the Arduino, which subsequently powers the accelerometers. The Arduino Mega Rev 3 is the board we chose as it was compatible with all the accessories as well as the motor control boards. Phases 2 and 3 are identical and reside in each leg. From the DeWalt 20-volt batteries, power flows through an adapter and onto the motor control boards. These boards were selected as they are compatible with the motors as well as the Arduino. These boards send power to the motors as needed and regulate the speed, RPM, and torque of the motors. Here is an in-depth look at our wiring between the Arduino control board and the accelerometers.
The implementation of an exoskeleton in a work environment that involves climbing and repairing power lines presents numerous health and safety constraints. The presence of powered motors attached to the joints of a person raises concerns for the potential for injury in such a vulnerable area. Additionally, the physically demanding nature of this work poses risks, including musculoskeletal injuries, high voltage exposure, and the dangers inherent in climbing high poles. To ensure the safety of the exoskeleton system, it is imperative that throughout testing and verification processes are conducted prior to its use on human subjects. The incorporation of components such as motors and batteries necessitate the consideration of potential risks such as overheating or explosions, which must be mitigated through proper regulations and testing procedures. The design of the exoskeleton should also include cooling systems to prevent component overheating in addition to adhering to established regulations and procedures. Ultimately, the goal is to reduce health and safety risk while enhancing the health benefits of the exoskeleton technology.
There are many related standards to consider when working on a project as large as this. Some of the standards that we had to consider were the ISO TC 299, which defines many robotics terms, the F48.91, which defines a lot of terminology for exoskeletons and exosuits, the IEC/EN, which defines a lot of efficiency standards and defining standards for electric motors, the JWG9, which defines a lot of medical equipment that is related to robotics and electronics, and finally the F48.01, which is the Exoskeleton Design and Manufacturing Standard. This was one of the most important ones that we had to consider, as the F48.01 standard discusses the design of the exoskeleton with a particular focus on the functional components. This standard ensures that the structural integrity of the design is at an adequate level to prevent failure and potential harm to a user of the exoskeleton. This standard also discusses the electrical components such as the embedded components and energy system to have an understanding of what the maximum and minimum requirements are to run certain types of exoskeletons. The cooling aspects are also considered in this standard. The software is mentioned in these standards to ensure that there are enough safety measures taken in the software side if there is an electronic failure. The software can notice it and activate a failsafe. In a project this large, There were many successes and difficulties throughout the process. The team was able to meet all of the deadlines that were set during the last 2 semesters for all videos and documentation that were required. We were also able to coordinate very well with our advisors, both electrical and mechanical, our mechanical team, and our sponsors. This was accomplished through regular meetings and constant communication between everyone. The team had success building the initial frame prototype by integrating our designs into the designs created by the mechanical engineering team. We were also able to accomplish a very important set of benchtop testing, which provided proof of concept and many important variables needed, such as current and duty cycle, as well as safety checks prior to testing the system on a person. Our final and biggest success was the final build and test of the full system assembly. This took weeks of long and hard work to accomplish, but the system functioned as well as we could have ever hoped. Some of the difficulties we saw were when interfacing with a second team from a different discipline. The mechanical engineering team was in Senior Design 2 as we were in Senior Design 1, which meant they already had a fully formulated plan and design as we were first understanding the project. As they were from the mechanical school, they also had a much different set of requirements and documentation that needed to be complete. After our first semester, we then had to take over the full project ourselves without much mechanical support outside of our advisor. One of our biggest issues was ordering and receiving parts in a timely manner due to budgeting complications and the supply chain. Our arguably largest difficulty was interfacing the Arduino PPM signals directly with the motor control boards. This concept is not often achieved the way we had designed, and took a long time to understand the full process of how to connect the components and send the correct signals to arm and run the motors. Our last difficulty was taking all of the programs created throughout the process of the project and compiling them into the final software. This required a long period of adjusting the program with the full system and many rounds of testing to fine-tune the system while being used by a person. Overall, with all of the successes and difficulties, the team is very happy and proud of how the project came together as a whole.
Now to discuss the budget. We were able to build the entire lower body exoskeleton for less than $1,000. I cannot overstate how instrumental the Innovation Lab was in our project's success. We were able to utilize many of their free resources, which helped us to complete the project while staying well under budget. A majority of the parts we used for the initial benchtop test were actually from the parts given to us or printed from one of their machines. The frame utilized many of the resources from the previous senior design team as well, which helped us keep costs low. Now, we are happy with the current progress of this exoskeleton, but there is always room for growth, and we have listed a few improvements that we would like to see implemented in the future. Firstly, we plan to improve the hip design. The current design works well, but we believe that there is potential to optimize it further to provide even greater support and stability to the workers. By using more advanced materials and a more ergonomic design, we can make this exoskeleton even more comfortable and practical for long-term use. Secondly, we plan to implement a PCB or printed circuit board in the control system. This will provide a more precise control over the exoskeleton movements, making it even more responsive and effective. With a PCB, we could also improve the accuracy of the sensors and data processing, which could lead to better overall performance as well. Thirdly, we plan to improve the cable building and management. Currently, the cables are somewhat cumbersome and can be difficult to manage. By improving the cable management system, we can make the exoskeleton even more user-friendly and easier to operate. Finally, we plan to fabricate the official metal frame. While we were able to build a functional frame using our existing resources, we believe that an official metal frame would provide even more greater support and durability. By working with professional fabricators, we can ensure that the frame is made of the highest possible standards with a focus on both strength and ergonomics. Overall, we believe that these future improvements will help us to build an even better exoskeleton that will exceed the current needs. Our team took great pride in the work that we have accomplished thus far, and we are confident that our lower body exoskeleton has the potential to revolutionize the power industry. We are grateful for the opportunity to work on such an innovative project for Florida Power and Light, and look forward to its continued success in pushing the boundaries of what is possible with this current technology. Thank you.